At the end of the topic, you will be able to explain the principle of a concave mirror, discuss the characteristics of the image formed by concave mirror, determine the focal length of concave mirror, list down the uses of concave mirror, describe the image formation by convex mirrors, explain the characteristics of image formed by convex mirrors, list down the uses of convex mirrors. We begin every day with light. We see many things around us. Light is a part of life to survive. We see shining objects, glittering objects, and brilliance of precious stones and so on. Do you know the reason behind them? Yes, it is due to the reflection, refraction, and many more phenomena of light. Scientists had actually tried to explain the nature of light and its various phenomena. The reflection on a plane mirror follows two rules known as laws of reflection, and it deals with angles. To understand the angles, we need to imagine a single light ray striking a surface. This is the incident ray. The ray bouncing off the surface is the reflected ray. We can draw a perpendicular line for the surface of mirror at the point of incidence. Now, the law of reflection states that the incident ray, the reflected ray, and the normal at the point of incidence lie on the same plane. Further, it states that the angle of incidence is equal to the angle of reflection, where I is the angle of incidence and R the angle of reflection. We know plane mirror form images of size equal to size of objects and at the same distance from the mirror. If we need enlarged or diminished image, how do we get it? Yes, spherical mirrors can be used to produce enlarged or diminished images. A spherical mirror is a curved surface mirror that has the same shape of portion of large sphere. The mirror surface that is bulging outward is called a convex surface, and the inner curved surface is called the concave surface. How do you decide if a mirror is concave or convex? If the outer surface of the section reflects, then the mirror is convex mirror. However, if the inside surface reflects, then the mirror is concave. Convex mirror produces diminished image, whereas concave mirror produces both diminished and enlarged image. We will learn the concept of light ray in a concave mirror and characteristics of image formed by concave mirror in the following slide. Let us discuss the important terms associated with the concave mirror. Consider a concave mirror AB. The center of the concave mirror P is called as pole of the mirror. Using the curvature of the mirror, we can complete a circle. And PC, the radius of that circle, is called the radius of curvature. The center of the sphere C is the center of curvature. The straight line passing through P and C is the principal axis of the mirror. The laws of reflection holds good for all reflecting surfaces, either plane or curved. For instance, a parallel beam of light that is parallel to the principal axis incident on the concave mirror gets reflected. All the reflected rays either meet or appear to meet a point on the principal axis called the principal focus F of the mirror. The distance from the pole of the mirror to the principal focus is the focal length of the concave mirror. Draw a normal line OC from the point of reflection at the mirror to the center of curvature. The angle XOC is the incident angle. The angle COY is the reflected angle. Convex mirror also have the following terms used to describe the image formation as that of concave mirror. Pole of mirror P center of curvature C, radius of curvature R, principal axis OP, principal focus and focal length. Let us now see how images are formed in a concave mirror for objects at a larger distance. A parallel beam of light originating from a distant object like a lighthouse after reflection of the mirror meet at the focal plane to form the image. This image can be obtained on the screen and hence a real image. The image formed has several characteristics. The size of the image is lesser than the size of the object. Since the parallel beam of light exactly meet at a point, it forms a real image. The image formed on the screen is upside down, that is, an inverted image. The distance between the mirror and the screen gives the focal length of the concave mirror. Now, let us discuss the nature of the image formed due to the position of object. Look at the difference in the given images. According to these images, when a real object is placed between the center of curvature and the focus of the mirror, the object AB has its image A', B' formed beyond the center of curvature. This image is real, inverted, and enlarged. On the contrary, when the object is placed between the pole and the focus, the object AB has its image A', B' formed behind the mirror and is virtual, erect, and enlarged. The given table details the nature of images obtained for different positions of the object. See this animation to understand more. Concave mirrors find various uses in day-to-day life. You can use concave mirrors to magnify the images formed on it. They are used as reflectors on the headlight of vehicles. Dentists and ENT specialists use concave mirrors to check inner parts of ear, throat, and nose. They are used in satellite dishes to collect energy for TV sets. The concave shape of a bat's ear helps it to collect sound energy. They are also used in telescopes to view distant objects.
Convex mirror always forms a virtual, erect and a diminished image irrespective of the position of the object. The given table details the nature, size and position of the image for two different positions of the object.
Let's look at the uses of convex mirrors. As they produce virtual, upright, diminished images, convex mirrors are used in the rear view mirror of vehicles to get a view of the road behind the vehicles approaching to the right. They are also used as security mirrors in shops as it covers wider area than our naked eye. Similar to concave mirrors, convex mirrors are also used in telescopes.
While dealing with the reflection of light by spherical mirrors, we shall follow a set of sign conventions called the new Cartesian sign convention. In this convention, the pole P of the mirror is taken as the origin. The principal axis of the mirror is taken as the x-axis, x-x of the coordinate system. The conventions are as follows. The object is always placed to the left of the mirror. All distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin along plus x-axis are taken as positive, while those measured to the left of the origin along minus x-axis are taken as negative. Distances measured perpendicular to and above the principal axis along plus y-axis are taken as positive. Distances measured perpendicular to and below the principal axis along minus y-axis are taken as negative. In a spherical mirror, the distance of the object from its pole is called the object distance u. The distance of the image from the pole of the mirror is called the image distance v. You already know that the distance of the principal focus from the pole is called the focal length f. There is a relationship between these three quantities given by the mirror formula, which is expressed as. This formula is valid in all situations for all spherical mirrors for all positions of the object. You must use the new Cartesian sign convention while substituting numerical values for u, v, f and r in the mirror formula for solving problems. In this topic, you have learnt, according to the laws of reflection of light, the angle of incidence is equal to the angle of reflection. The incident ray, the normal to the mirror at the point of incidence, and the reflected ray all lie in the same plane. A spherical mirror whose reflecting surface is curved inwards is called a concave mirror, and mirrors with reflecting surface curved outwards is called a convex mirror. The center of the reflecting surface of a spherical mirror is a point called the pole P. The reflecting surface of a spherical mirror forms a part of a sphere, and the center of the sphere is called the center of curvature of the spherical mirror. The radius of the sphere of which the reflecting surface of a spherical mirror forms a part is called the radius of curvature of the mirror. For spherical mirrors of small apertures, the radius of curvature is found to be equal to twice the focal length r, which is equal to 2f.
At the end of the topic, you will be able to define refraction, explain the laws of refraction, determine refractive index of a medium. What happens when you insert half the length of a stick inside water? Yes, the stick appears to be bent due to refraction of light. Light travels in a straight line only when it moves in a single medium. Its velocity is maximum and constant in vacuum. When light travels from one medium to another, it bends at the surface of separation. This happens because the velocity, that is, its speed as well as direction, changes at the surface of separation of the two media. This phenomenon is refraction of light. See the animation to understand refraction. Let us look at the reasons for refraction. Velocity of light depends on the density of medium. The velocity of light in water is less than that of air. The reason is water is denser than air. Hence, light travels slow in dense medium. When light ray traveling in a certain medium enters another medium, they bend at the surface of separation due to change in its velocity. That is, the velocity reduces when the light enters from a rarer medium to a denser medium. See this animation to know more. Now we will discuss the angle of refraction. We have learnt when light passes from rarer medium to denser medium, it bends. The angle of refraction measured with reference to the normal line. Remember, normal line is the imaginary line drawn perpendicular to the surface of separation of two media. The angle between the refracted light ray to the normal line is the angle of refraction. On the other hand, if the light travels from denser medium to rarer medium, it bends away from the normal line. The velocity of light increases when it travels from denser medium to rarer medium. The refraction of light is described by two laws of refraction. The first law of refraction is the relation between the incident angle and the refracted angle of light to the normal line drawn on the surface of separation. It states that the ratio of sine of angle of incidence in the first medium and the sine angle of refraction in the second medium is constant. This constant is the refractive index mu of the second medium with respect to the first medium. The law can be expressed as sin I by sin r is equal to 1 mu 2. This law is also called as Snell's law. Using this relation, we can calculate the refractive indices of different substances. The second law of refraction states that the incident ray, refracted ray, and the normal line drawn at the surface of separation of media lies on the same plane. Let us discuss an experiment to determine the refractive index of a glass slab. Take a glass slab, place it on a drawing paper. Draw the outline of the slab with pencil. Remove the glass slab and label A, B, C, D. Draw a normal line N to the face AB. Mark the point O. Now draw an incident ray at an angle, say 30 degrees to the normal. Fix two pins P and Q on the incident ray. Place the slab and observe images of P and Q at the side CD. Now fix two more pins R and S along the refracted line, so all pins must align in a straight line. Remove the glass slab. Now join RS with O'. Also connect O' and O with a line. Now measure the refracted angle R. Repeat the experiment for different incident angles, say 35 degrees, 40 degrees, 45 degrees, 50 degrees, and so on. Find the refracted angle and tabulate them. Then find the ratio of sine of incident and refracted angles. You observe that the value sin I by sin R is constant. The average value of sin I by sin R is the refractive index of the glass slab. In this topic, you have learned velocity of light decreases in denser medium. The bending of light rays when it travels from one medium to the other is refraction of light. The ratio of sine of angle of incidence and the sine of angle of refraction is constant.